Hello everyone. Thank you, TEDxIISERBPR, for inviting me to this beautiful event. I feel deeply honored. I'll be discussing two important issues: the challenges of coastal ocean studies and the intricacies involved in the interaction between ocean and monsoon. But the challenges we face in coastal ocean studies is a bit huge than the challenge that I have taken up now as the vice chancellor of a university established just 1 year back in the tribal heartland of Odisha and in the mineral-rich districts of Odisha, that is called Keonjhar. So these are the important coastal processes studies we have undertaken since 2008 while I was serving as a professor at the Department of Marine Sciences, Berhampur University. Some of these studies were taken off by sponsored projects, both R&D projects and consultancy projects, but through which we developed our facilities and laboratory, and also the students were trained. Friends, ocean science teaches us a great lesson. Ocean waves rise and fall in a natural region. When ocean wave rises, it hints that a fall is imminent. But it also carries promise that it will rise again. So that suggests, or we learn from this, that if we take the challenge, we have definitely some opportunity. So let me tell you what are the challenges we faced while taking these studies. For the first time along Odisha coast, there was no observation of oceanographic processes, particularly coastal oceanographic processes. We have a massive deployment of wave radar buoy, tide gauges, current meter, and continuous profiling, coastal profiling of beach profiles, sediment characteristics over the entire coast at a very high resolution at every 500-meter interval. But the most difficult observation or most the difficult challenge was taking the bathymetry. See, bathymetry observation along the coast is difficult because we have to take the help of a ship or a mechanized boat to study the bathymetry. But the problem lies with the nearshore environment between 0 to 5 meter. So that is the limitation of our study. Even today, we are not able to determine the bathymetry of the nearshore environment because of the very strong, oceanographic activity and the region which we call as the surf zone and the turbulence at the surf zone. Even the satellite observations do not help in the surf zone. So to our interesting observation, when we analyzed the waves, we saw that the waves are unidirectional around the year. Waves are forced by the wind. Wind changes direction with season, but waves approaching the coast are unidirectional around the year. And the energy of the wave is maximum during the monsoon season, followed by the pre-monsoon season, whereas this period the wave energy is less. So that is how the observation during the monsoon and pre-monsoon is extremely difficult, particularly in the nearshore region or in the coastal ocean. So these are the other observations that continued, like tidal observations. And from the tidal observations, we could see that the tides along the coast is semi-diurnal in nature. From the tidal form number we computed. Similarly, we also studied the ocean currents. and southerly currents were dominant all along. Again, this is called the sediment transport along the coast. See, the sediment which moves along the coast are wave induced, and waves, as you see, is unidirectional from south-southeast direction, and it induces sediment transport from south to north around the earth. But the transport is again highly complicated during the at the estuary points. So this is an example of transport, sediment transport at the Rushikulla estuary, the world famous turtle nesting beach, where the transport is toward the shore during the northeast monsoon, and the transport is offshore toward the southwest monsoon. So this kind of transport creates erosion and accretion in the course of the annual cycle. And then we also studied the impact of this, transport, sediment transport due to coastal structure. This is just an example of Dhamra Port. Prior to the development of Dhamra Port, you can see the shoreline here is completely negative. That means it was an erosional environment. And subsequently, after the construction of Dhamra Port, I would tell you, it is a natural port. There is no, breakwater. Panika Island serves as the natural breakwater for Dhamra Port, but only construction is jetties. But even there, the sediment transports or the environment there changes from the erosional environment to the depositional environment. And then we studied the entire erosion and depositional environment, major hotspots of erosion and accretion along Odisha coast at a very high resolution and every 500-meter interval, and then identified those regions. And then we wanted to do some modeling studies using some models of the DHI, Danish Hydraulic Limited. One is lead drip, which is used for sediment transport modeling, and another is lead line, which is used for shoreline prediction. These models, we could see that they have certain limitations, and the limitations are inherent because of the inherent errors in the bathymetry, because all these models, initial data which goes is bathymetry is extremely important. Since we did not have bathymetry observations in the near shore environment, so models had their inherent error, and therefore they have certain limitations. So it is again a challenge for the scientific community how to overcome these limitations so that you can have observations of the near shore bathymetry, and then you can have a very high resolution model of coastal profiles so that your models will be more accurate. And here after studying some of the things, we could see that the waves which are unidirectional, they transport the sediment from south to north. But the problem there again lies that when the wave approaches the coast, they get refracted, and this wave refraction is dependent on the shallow water region and the bathymetry. So there also, if you don't have bathymetry observations near the coast, that poses serious challenge for the coastal modelers. So alternative approach we have suggested here, we can run a morphodynamic model with very high resolution to resolve some of these issues. And also, if you have a observed database, you can link with Google Earth so that, or Java web portal, so that you can see it in Google Earth and then compare your model observations with simulations. And coming to the other aspects, like role of ocean in Indian monsoon variability. This study I was doing during my PhD at IIT Delhi, and this is my first paper published during my PhD, we could reveal that the monsoon has three distinct branches over Arabian Sea, Bay of Bengal, and South China Sea. And these branches are revealed in three different fields like pseudostress, latent heat flux, and surface pressure. Subsequently, when I was doing my as a Commonwealth Fellow, I worked at the University of Reading and worked on intra-seasonal variability of monsoon. Active break cycle is an important feature of intra-seasonal variability. And the question here is whether ocean drives the monsoon or monsoon drives the ocean. So they are coupled systems. They evolve dynamically, they respond to each other, and they influence each other. That is what is we could see. And that this picture also explains that even monsoon has its own internal dynamics, and it is also affected by some of the external forcings like El Nino and La Nina. You can see during El Nino, the monsoon fails, and during La Nina, monsoon behaves. But this relationship is gradually weakening. And this is the active break cycle of the monsoon. This northward propagation is the active break cycle, whereas the eastward propagation is called as the Madden-Julian oscillation. And this intra-seasonal oscillation of monsoon has basically two important modes of variability. One is the 10 to 20 day mode, another is the 30 to 60 day mode. 10 to 20 day mode is propagates westward in the Indian latitude, whereas 30 to 60 day mode, as I showed you, propagates northward and eastward. So our focus was to study active break cycle, that is northward propagation of intra-seasonal oscillation. So we took the Hadley Center model. It's a coupled model, very high resolution model. And then we took the Euler as the proxy and then compared the model simulations with observations. You can see they compare very well, particularly when you take HCM3. And this is the flux average model. Flux average means when we take the land use land cover as average. So land use land cover also plays a very important role in climate model or climate system. So that is how you can see that only HCM3 is comparing well, whereas HCM3 FA, that is flux average, the comparison are not that good. So we studied the evolution of the active break cycle, and the purpose was to see whether we can get any signals of predictive signals. Suppose we get some signals before 5 days, so that means we can predict the event, whether active or break, before 5 days. And we did get some signals from different fields. We analyzed different ocean fields, and then we could also get some signals so that it could have a predictive skill. And the major challenges in a coupled model is to see how the dynamic and thermodynamic forcings they interact with the active break cycle. That is how we examine the mixed layer depth and the thermodynamic thermohaline. This is called isotherms. B20 is the isotherms at 20 meter depth. So during the active phase, what happens is the entire ocean, Arabian Sea and Bay of Bengal gets warm, and the mixed layer deepens. And then there is a transfer of energy from the surface to the thermocline depth. So that is very important in making the evolution of the active break cycle. And after having seen that active break cycle is one of the very important events and has directly linked with the agricultural system and economy of the country, we wanted to see whether if we can link the crop with the climate, that would help the entire farming community as well as the nation. So there are many intricate linkages between the crop and the climate, all of you know. And then if there is increase of air, there is accelerated crop growth. The length of the growing season is reducing because of the increase in air temperature. So these are some of the very complicated, response of climate system or crop response to climate system, and then to mitigate and to strategies, devise strategy for adaptation and mitigation to reduce the vulnerability of climate change. We should have a very accurate crop climate coupled model, and that is what we wanted, and we tried here under different controlled conditions. Then when the carbon dioxide is 1.5 times more, when it is 2 times more, and when it is 2.5 times more. So this is, we could say that there is a 10 to 40% loss in productivity in a warmer environment. And similarly, for irrigated rice and rain-fed rice along the Indian coastal zone, there is also 15% loss increase along east coast and 20% decrease along west coast. So the stress is more along the west coast than east coast. Similarly, irrigated maize crops are likely to have yield loss between 15 to 15%, while rain-fed maize shall have a yield loss by 35%. So these are some of the very interesting things which are revealed, and therefore we should have a very accurate crop climate model, coupled model to simulate the future of crop productivity and to cope, which will pave way for a sustainable agricultural production. Thank you, friends. And this thank you slide that I wanted to explain the nature, the force of the nature. You see the wind, this is very near to the Gopalpur. The wind has changed the direction of the trees.